Hello. So here we are. So it's such an honor for me to present in front of the whole Rails world, maybe half of Rails world. But anyway, it's a 20th Rails anniversary, so 20 years. 20 years ago, I had no idea what programming is. I didn't even have a computer. And my only passion was music. And I still remember that feeling of buying a new tape or CD and looking through the track list of a new released album and trying to guess what the song will sound like and what's going to be about. That's kind of a pleasant feeling of anticipation. So I put the track list of my today's talk, Untangling Cables and Demystifying Twisted Transistors, on the first slide, so you can build your own expectations. And we can see in the end whether I match them or not, whether you guessed what they're going to talk about or not. So let's play this game. And we start with the first track called It's Rails. And I want to talk about a bit about the reason why we are here. So hundreds of people came to Amsterdam from all over the world these days, not to enjoy like museums, canals, other local entertainments, but to spend 2 days talking about the craft of software engineering. That's amazing. That even sounds a bit like a cult, but that's okay, right? I'm good with it. So just because Rails is not just a tool, it's not just a framework, it's also a software development philosophy. It has conventions, it has principles, it has the doctrine, the Rails way. And one of the cornerstones of this philosophy is conceptual compression. Rails does its best to hide all the complexity inside the black boxes of its components to let you focus on what's important for your application, for your product. On the other hand, like black boxes are good, but you should master your tools to become a better version of yourself as an engineer. And that means you should find some brevity and take a look inside the boxes. And today, I'd like to help you in doing this for one particular box, the action cable box. We're going to open it today. So, a couple words about myself. My name is Vladimir or Vova, and you may know me by my GitHub handle, Pelkan. This is my primary social networking tool. So if you want to reach out, just file an issue. I work at a company called Evil Martians. We're a product development consultancy, which you also probably heard of. We have a really cool blog. We build amazing web products. We're really good in Rails, so if you need some help, just come to me or my colleagues being here. So yeah, we can help everyone. And I also work on AnyCable, a real-time server that can be used as a drop-in replacement for Action Cable to bring new features and better performance and so on. However, I'm not talking about AnyCable today, surprise. I'm actually talking about Rails, because it's a Rails world. But you can still spot AnyCable in between the lines, for sure. So, last but not least, I recently published a book on Rails and abstractions. We have in Rails and for Rails. And that's actually leads us to the start of the Action Cable exploration, because the the exterior of the black box, the wrapping we have, is an abstraction that Rails gives us. That's the interface of the framework. And I'd like to start by looking at the Action Cable box and what we have outside of it, what we see as developers, how we use it. Let's just recall how Action Cable works, its interface and its abstractions. So the primary abstraction of Action Cable is a channel. So we have a kind of channels layers. Its primary purpose is to manage real-time stream subscriptions. It's like a controller, but for real-time communications. It has very familiar conventions and interface similar to other parts of Rails. Let's take a look at a full-stack example. So that's basically everything you need to get started with real-time on Rails. Just a single Ruby class with some business logic and a bit of JavaScript code to establish a communication channel. You don't need to know about WebSockets, all the underlying low-level stuff. It's hidden from you because all you use is a set of abstractions provided by the framework. That's the goal of the proper abstraction, to hide the complexity. That's a where conceptual compression takes place. Channel subtraction is just a part of the action cable equation. Even in the original presentation back in 2015, we can see some other components present. But that's just the tip of the iceberg of what action cable is. The real kind of a map of action cable would look like this. It's a bit more complicated and hardly readable from a single slide, but no worries. I'm going to navigate you through this map today. That's our goal. We're going to learn about it and see how this design affects the interesting side effects and phenomena we see when using action cable. And I would like to start with the client-side part of this map. So we already seen some client-side code. It's an example of code which use the unofficial Rails action cable library. So we're talking about what Rails provides out of the box. And it comes with a couple of kind of abstraction. First, as a consumer, it's a kind of WebSocket wrapper. And another abstraction is a subscription. It's an object that receives updates from the server based on the parameters we pass to it. Basically, the name of the channel and some additional data. So one consumer is assumed to be used by a single user session, where a session is usually a browser tab or a mobile device. We don't need multiple connections for different channels, for example. It's just a single connection. I just want to add a quick note regarding the browsers. There is a cool project called Cable Shared Worker, which makes a session, like a cable session, shared across the whole browser. It's very useful when your users prefer to keep tabs open and adds more and more connections, which adds additional overhead for the server. You can use this library to kind of reuse a single connection for all of them. So a session is not only just a browser page, but it can be just a browser session in terms of a browser. Then we have subscriptions, and we may have many of them. They're all internally multiplexed. That means that all the messages for different subscriptions are coming through the same WebSocket connection. From the WebSocket point of view, it has no idea of subscriptions, channels, or whatever. It just operates on messages. At the client-side library responsibility to roll this data into proper JavaScript objects. But the question is, the first question that I would like to discuss, how many subscriptions we may have? Is there any overhead of using them or whatever? Since they're just abstractions, like just JavaScript objects, can we just have tons of them? Well, the short answer, that's just the beginning actually, the full version will take the whole talk. So yes, you can. Like in theory, the design of the library and action cable and the protocol or whatever doesn't restrict you on the number of subscriptions you have. But as we will see in the very end of the talk, there are some things that we may need to consider when dealing with it. One interesting fact that, given that subscriptions is just abstraction at the client side, we may even have duplicate subscriptions. So we can subscribe to the same channel multiple times, for example, from different front-end components. We don't need to think about whether there is already a subscription or not. Everything is solved within the client. So it's smart enough to create the actual subscription on the server side just once for multiple channels and just route messages to all of them, and similarly unsubscribe whenever no one needs it anymore. So the last piece of the client is the monitor. It's an important part. So Action Cable doesn't only give you wrapper over WebSocket and this subscription API, it also tries to make sure that your connection stays alive when you have some network problems and whatever. The way monitor works is as follows. So it actually solves two things. The biggest problem with persistent connections is how to identify that the connection is broken. Since underlying connection is WebSockets using TCP, okay, sorry, it's going to be a bit too low. But anyway, the thing is, if we do not send any data in any direction, we cannot know if there is a connection or not. That's how TCP works. So it allows you to have arbitrarily long gaps in data transmission and still assume that connection is alive. To handle this, WebSocket server, Action Cable server, sends ping messages every 3 seconds by default. And the monitor keeps track of how long time ago the last ping has been received. So it maintains a timer, and if a ping received before the timer finishes, it's just getting reset. But if we do not receive pings for a specified amount of time, the monitor just issues a reconnection and enforce the client to try to reestablish connection and figure out whether the server is still available or not. Is there an intermediate problem, or it's just a persistent one? So, as I said, pings are meant to identify broken connections. They work most of the time, but not always. There are some exclusions related to some proxy servers and intermediate representations where we can solve them by using pongs in response to pings, but that's something that is missing from Action Cable right now. And another thing I want to pay attention to is that, as I already said, pings have a pre-configured interval, like every 3 seconds. And it turned out that for mobile devices, especially kind of a cheaper mobile devices with less powerful batteries, it can be really resource-consuming in terms of battery power, because if the application using WebSockets and it has to wake up every 3 seconds to consume this message, it just wastes CPU cycles. So it's very useful to configure the ping interval to be higher. And unfortunately, with Action Cable, there is not that easy. You have to do some monkey patching at the both sides of the cable, so the client side code at the server side. It's possible, but you can do this only for all the connections, for every one connection. There's no way to redefine ping interval for any particular connection, for example, yet, at least. That's some of the limitations of both of the client and the server. And if you feel that client is not that flexible, you can try alternative clients. We have any cable client, which has very different architecture and extensible, flexible. I'm not talking about any cable today. And you can write your own. That's the more interesting part. So why you can write your own? Just because Action Cable is actually not just a tool, not just a framework, it's a protocol. So it's a protocol of communication between the server and the client. And you can implement client in any language or whatever, and if it implements the protocol, it will be compatible with your server. Similarly, you can build a custom server and use it with Action Cable client. So it works in both ways. The formal specification of the protocol is available at any cable website. Yeah, any cable. It's missing on the Rails docs. I hope it will find its home in the new Rails documentation eventually. But for now, if you want to build a custom protocol, for example, if your platform doesn't support Action Cable yet, you can just look at the specification and implement it. It's not that complex. It describes just a few different types of messages. There are commands on the left side that are messages which clients send to server. And these are messages from the server to client, like we can call them types probably. Most of them have type field, and just 5 of them also. Some messages do not have types. So the protocol is not, I would say, complete compared to other real-time protocols. We actually missing a lot of stuff that could be useful. We do not have identifiers, neither for sessions nor for messages, and that makes it harder to implement such features as presence tracking, history support for streams, and so on. We do not have proper acknowledgements for perform actions, and we do not have error handling. That's the most intriguing part, because there are situations when your Action Cable server side just fails to process an incoming command. The problem is there is no response back to the client of what's happened, and the client just doesn't know about it. Let's consider an example. It may seem that it's too synthetic. It cannot happen in real life. No one writes code like this. But we will see that actually based on the real world usage of Action Cable and some other frameworks. So what we do here, we create subscription and unsubscribe immediately after that. That results in sending subscribe and unsubscribe command one after another. And in the end, we finally decide, OK, we want to subscribe. So the final call is creating subscription. And we expect this subscription to be established. The question is, will the client be subscribed or not in the end of this code execution? And the answer is, well, let's see what the answer. And to see what's going to happen, we're going to use emulation. We will write a scenario emulating this code using a tool called WebSocket Director. It's one of the tools you can use to play with WebSocket scenarios, so it allows you to write fixtures in YAML. So you just define the messages you want to send and expect to receive. It's something like VCR, like fixtures, maybe. So you can use them to play with your WebSocket server. And you can run scenario concurrently using multiple clients. That's what I'm going to do. So I run this scenario using 10 clients. On the right-hand side, I have a server logs. And we see a bunch of exceptions. Client side, we see that some clients failed to execute the scenario. So 2 out of 10 were not subscribed to the channel in the end. 8 out of 10 were subscribed. So there is some randomness. But what's interesting is the exceptions we observe. So sometimes we see that no subscriptions with this identifier. That means that unsubscribe commands were processed before subscribed. And another situation, already subscribed. That means that 2 subscribe commands were processed in a row by the server, but we send them interchangeably. That means there is a race condition situation somewhere at the server, right? But that's what we're going to explore in a minute. But now I want just to demonstrate how Rails deals with this exception handling problem. Since we do not have exceptions, we just keep trying to subscribe until we receive rejection or confirmation. And in real life, that means that a client may continue subscribing indefinitely. And you can see this in some Rails applications out there. I don't know, like, it's just a bunch of waste of like server resources to handle this commands, which are not doing anything, just raising exceptions, or silently ignored, probably. Some of the code paths and action cable just ignores some edge cases. So why does this happen? And that leads us to the core piece of the talk, threaded transistor. Yes, let's take a look at this part of the map where we go through the whole process of handling WebSocket lifecycle events like open, close, and incoming messages. So first of all, there is an HTTP connection established between a client and a server. Your web server, it can be Puma, Unicorn, Pitchfork, whatever. But then the underlying socket object is hijacked using a rec hijack mechanism, and from now on, it's managed by the action cable server. It's kind of a singleton object in your application. Then it does some utility work just to add it to the event loop to consume, just to monitor active WebSockets and send data back to them. And as soon as the connection is established, it issues the event, open event. And now we enters the kind of a main executor part of the Rails server, which handles all the WebSocket communication. So first of all, there is a worker pool. There's a threaded executor pool from concurrent Ruby. It has a queue of tasks, unlimited. So it's not blocking. You can always send subtasks into it, and they're going to be eventually processed. And it has just, by default, 4 threads to handle all the work. Every unit of work is executed within the Rails executor context. We're going to talk about it in a minute, but it's an important component too. And finally, it reached your application code and invokes the corresponding callback. For example, open translates into connection connect, then subscribe message translates into creation of the channel object and subscribe callback, and so on. So we handle incoming messages, and we handle the connection closure in a similar way. All the code paths are about the same. They all go from this worker pool. So what do we need to know about it? First of all, we need to know the size of this worker pool, its existence, the way the incoming commands are processed. So they just process concurrently. There is no kind of a log or queue for a particular connection. So if we receive 4 commands from the same client, they just process concurrently by 4 threads. That's why we see the subscribe and unsubscribe race conditions. What's important is that we need to take this thread executor pool into account when we deal with shared resources. For example, database pool. So if you have Puma serving your application with like 5 threads, and you have action cable also a part of the same process, your total database pool size must be at least 5 plus 4, 9. Otherwise, you will hit the contention at the database pool level because the default is usually the same as the number of threads in the web process, like 5, right, Rails max threads. But it doesn't take into account the action cable pool size. You need to know about it, at least because it may lead to callbacks executed within action cable to be slower than it could be. And yeah, as I said, it uses Rails executor. Rails executor is an internal component which is responsible for performing some cleanup work for unit of works, for example, HTTP request or background job execution. One of the examples is releasing database connections back to the pool at the end of the HTTP request, similarly at the end of the action cable work. And another example is resetting current attributes. That's what I want to talk about a bit in more detail. So we know that connection object established and lives for the whole lifetime of the socket. So it's kind of a lives while the connection is alive. You may want to set the current attribute for this connection right in the connect callback and rely on it in your channels and other methods executed within this connection context. But unfortunately, connection is not an execution context. It's not an execution boundary. The executor will reset everything at the end of this call. And you need to take care of it, for example, using command callbacks, which were added, I believe, in Rails 7, not that long time ago. And you can set up the execution context for every connection. So the context, the execution context of the connection and the connection itself has different lifetimes. So the connection is long-lived, but the execution context is set up and reset for every interaction. So what kind of units of work we have within this threaded pool? As I said, lifecycle callbacks, incoming commands, and outgoing messages as well. And that leads us to the part responsible for broadcasting. So what do we have here? Yeah, some known parts, some new parts. Let's track the path of the message we broadcast from the application and how it reaches the client in the end. So there is a pub service. It can be an external system like Redis or database. It can be the same process if you're using async adapter for some reason. Then it goes to some abstraction which handles the specific implementation logic. And this adapter maintains the map of subscribers. That's where the actual routing happens. So we have, it's mostly like a hash with a key, a stream name, and a value, a list of not clients, but callbacks. That's interesting. We do not store channel message instances or connection instances in this map, but we store procs, Ruby procs, because we can implement custom transmission handling using stream interceptors, which is not mentioned in this talk, but they exist. The interesting part here is that we have two pools here. One internal threaded pool, which just distribute the broadcasting work. It does not touch your application code, so you don't need to think about it a lot. But it exists and it still introduces a level of concurrency into the execution. Then everything goes back to the same worker pool, executor, channel, connection, and finally reads the client. What's important here? We have two kind of a concurrency branching here, two thread pools, and the same problem is going to appear here. We don't know the order of broadcasts will be at the end when we reach the client socket. We'll see that in action in a minute, but one important thing, there is no component responsible for keeping the broadcast message somewhere, like in memory, in cache, or whatever, to make it possible for clients to request it if they missed some messages during reconnection. There is just nothing. That's because by design, Action Cable provides at most once delivery guarantee. And that's pretty much it that I can tell today about this problem, because I have a very different talk on this topic, and I don't want to repeat myself. It's pretty new and it's still valid, so you can check it and see what are potential problems you may encounter as an application developer due to this limitation of Action Cable. So the talk is called Pitfalls of Real-Time Application, but I want to show a couple more pitfalls that we may encounter. So as I said in the diagram, we saw that there is a concurrency involved into the process of broadcasting data. So this is an example of how to see it in action. Let's see that we want to broadcast some data that must be delivered in the same sequence it was broadcasted. There could be such a situation. And the problem is, if we run the this code and we connect to the server. Here we're using Action Cable command line client just to see everything here. We can see that the actual order of messages received by the client is kind of non-deterministic. It's really not what we send to the Action Cable. And that's because we have all these levels of interactions within the processing pipeline. And, well, unless you have the size of the pool, like more than one, you cannot guarantee the order of messages delivered to clients in Action Cable, unfortunately. So there is one more example, kind of related to the previous one, but I know that many people stumble across it. You subscribe someone to a stream, you deliver the message immediately, and will it be arrived or not? I leave it up to you. So it's a good at-home exercise to write some scenario, maybe using WebSocket director, and see what's going to happen, because the results are interesting. It's much, like, I was surprised, actually. So enough talks about like threads. We are the Rails conference, not a RubyConf. So we need to talk about something higher level. Let's bubble up to the application level and talk about Turbo, because this is a Hotwire track, right? And we're going to talk about streams, turbo streams. So turbo streams. It's actually another black box which wraps the Action Cable black box. It compresses the kind of a concept even more. You don't need to write any Action Cable code to actually use it with Turbo. You just need to put HTML elements on the page. Like just a quick recap how it works. You add an HTML element, Turbo stream source. It automatically creates a connection and subscription to Action Cable. You can send broadcasts to it. They're going to be result in some DOM updates and some other stuff. And whenever the element disappears from the page, the unsubscribe command is issued, and the channel is removed from the list of channels of this connection. One thing I'd like to point to that, we still have the connection. Actually, if you don't have TurboStream elements on the page, the connection, if you once created the consumer, it's still alive. Well, maybe not a big deal. Maybe it is. I don't know. Like if you're using like TurboStream just for the single page, and like 99% of your application not using it, you may end up having all the clients connecting to the cable just for nothing, and just using some memory, whatever, at the server side for nothing. Just good to know. But the real problem with Turbo is the situation with subscribe, unsubscribe callbacks. That's actually the way it happens in real life. Because when you navigate with Turbo, especially with using Turbo preview mechanism, the process of adding and removing TurboStream elements from the DOM tree happens frequently. Sometimes it's the same element, just added and removed. And it results in calling subscribe and unsubscribe frequently. And that's the reason why this guarantor hack has been added to Rails, actually, just because Turbo relies on it. And another problem is that when you manage your subscriptions using HTML, you don't really know how many Turbo streams you have on a given page, especially if you use them in a kind of deeply nested partials. They could be everywhere, maybe in the tables or whatever. And you cannot control the number of stream elements. And some people think about it, like they're kind of afraid of having too many turbo streams on the page. So I stumbled across this question and I answered it. There's kind of a short version. It's not fit the slide, no worries. We're going to talk about it right now. That's the same question we talked about in the very beginning, but now we will finally reach the answer. So second for advertisement, I have the full answer already published in our newsletter called Any Cables Monthly, where we write about kind of news and updates related to real-time web applications development. And every issue contains some micro blog post on something new. For example, the question on too many streams. Like, is there such problem or not? And to understand when this problem happens, we need to discuss the situation when the reconnection happens, when this monitor kicks in and tries to reconnect our reestablish our WebSocket connection, and what's going to happen there. So, whoa, okay, yeah, that's something like that is going to happen. So imagine we have n clients, and we have a server start situation. So whenever we start a Rails server, we have to terminate all connections, and they will try to reconnect automatically. Now, let's assume that on average, each connection has m channels. Then now we know that every event, so open event, and every incoming command, subscribe command, is processed by this threaded executor pool. And now the queue size, the work queue size, is affected by both factors, by the number of connections and by the number of streams each connection tries to subscribe to. And the work queue is getting larger as more connections you have and more streams you have. Now the problem continues with the subscription guarantor or any other mechanism which tries to eliminate this lack of confirmations from server. So server is slow to respond with confirmation. Guarantor sends subscribe commands again like twice a second by default. And it just adds more and more tasks to this worker queue. And in the end, you may end up with server just stuck with processing useless commands, actually, because at the time they arrive, they probably won't be needed at all because the client might be disconnected. So that's an example of a classical software development performance problem called thundering herd. And in Rails context, in action cable context, and WebSockets context, I use the term connection avalanche. Well, as far as I remember, the first time I heard it actually was from David back in 2018 when we discussed action cable with Basecamp. I'm not sure what the original origin of this term, but anyway, we're going to use it. I like it, avalanche. Why not? So the connection avalanche leads to the significant load spikes. You may notice it if you have some instrumentation or APM servers. You will probably notice really like high CPU usage, memory usage, whatever, like slow down your requests and everything. It's just nightmare for you, especially if you didn't expect that. We need a way to protect Rails from connection avalanche. We need somehow kind of to build a snow shed, for example. And there are different ways to achieve this. Some are already built into Rails, some not yet, some you can build yourself. And I just want to quickly recall them. We're out of time, but anyway. So the first thing is what we can do, we can tell clients to not reconnect all at the same time, for example, when server starts, but add some randomization to the kind of a cooldown period they wait before trying to reconnect to the server. And that's something that has been fixed in Rails 7, because in Rails 6, for example, all the clients were trying to reconnect at the same time, introducing like one-time, really huge pressure on the server. Now it's kind of fixed. It can be better. You can see like any cable version has a better distribution, but we're good with it. Another two things, we know that action cable commands executed within the threaded pool, and there is a growing queue of tasks in it. We actually cannot monitor it even, like that's a problem. But anyway, try to merge subscription, use less channels, and make your subscribe calls faster. You can move your logic into perform calls, which are not expecting any confirmation from the server, and so you can wait indefinitely. That's one of the options. Another idea we employ sometimes is using serialization for subscribe commands. That's something that built into any cable client. It works with both Rails and any cable servers, doesn't matter. But it maintains a kind of a global log for subscriptions within the client, so it doesn't try to send 10 subscriptions one at a time, but one by one. This way we reduce the pressure on the server, and actually everything happens much faster than if we try to put them all at once. And finally, if you have large amount of traffic for both WebSockets and HTTP, it makes sense to isolate clusters, just because we still use Ruby, we still have GVL, and if your threaded pool executor for action cable commands is constantly doing some work, that means that like for example, Puma executor is not working as fast as you want because it still competes for Ruby for MRI resources. So it's a good practice to separate them. And well, we have some other options. Actually, just switching to any cable, we kind of solve this problem because we do not need to reconnect WebSockets on deployments. And we have some cool features to avoid resubscriptions at all. But that's kind of the beginning of another territory, another map I'm not going to talk about today, because it's very different from what we have an action cable, I can say that it solved most of the problem. It has its own, for sure, but it's just a different story, worth different kind of talk. Going back to this situation, I just want to say, like, let's keep this slide. I like it. Yeah, this one. So the founder inherit or avalanche problem is actually one of the biggest problems we have in action cable, which is really not affected by the really high load. You can face it at 1,000 of connections or 100 of connections if you have a smaller like instance size serving WebSockets. You just need to be prepared for it and know when it happens, how to deal with it. Because it's really based on all the things we learned along the way, like on the way action cable works internally, on this concurrent requests, on this threaded executors, and so on. And now you can at least understand why it happens. And how to solve it's a different problem, but, well, we have some ideas there. It's getting slow. So, yeah. I think that's it for today. I'm out of time. I have stickers. I will have slides of this link later. And thank you, everyone. And use your cables reasonably.